Okay. Hi. Good morning, everyone. My name is Shafin. I'm a PhD student at the Incorvia lab. Today, I'll be talking about antiferromagnetic tunnel junctions for Spintronics. So we know that data today is growing exponentially. Every minute, we have hundreds of hours of videos and millions of texts being generated and e-commerce transactions. So that poses some challenges for us. The first one is scalability. We need constant expansion of storage. And then there's also the challenge of energy consumption. So data centers today already contribute to 1% of global electricity consumption. And also they contribute to 2% of total carbon emissions. So there is a strong need for inventing new memory devices that are smaller, faster, and significantly more energy efficient. So that is why there is such a rise in research in magnetic tunnel junctions, but traditional ferromagnetic tunnel junctions have some key problems. The first one is that there's stray field in these devices. So the reference layer can emit stray magnetic fields that can unintentionally cause bit errors in the free layer. And then the second challenge is that due to the ferromagnetic resonance of the materials, the speed of these devices are constrained to the gigahertz range. So we need new materials and device concepts that can break these constraints, and that is where antiferromagnets come in. So here is an outline of the talk. So first, I will cover some of the fundamentals of antiferromagnets, focusing on collinear versus non-collinear versions. And then I will discuss readout mechanisms in non-collinear antiferromagnetic tunnel junctions, followed by how we can write to these devices. And finally, I will be summarizing these discussions. So onto the fundamentals now. So you can see that in antiferromagnets, the magnetic moments of atoms, they lie in opposite directions. So the net magnetization in these materials is 0. So instead of magnetization, the key state variable here in these materials is called the Neal vector. So the Neal vector essentially represents the relative orientation between opposing spins. So for example, in this copper, manganese, arsenic antiferromagnet, you can see that there are two sublattices of manganese, and the spins on these two sublattices are oriented opposite to each other. So if you consider this as like a 0 state, inverting the direction of each spin would produce the 1 state. So interestingly, for these types of materials, inverting the direction of each spin is essentially the same as inverting the atoms with respect to this green point in the middle, or by translating between the neighboring sublattices. And now, for these inversion and translation symmetries, the materials that have these symmetries are known as PT symmetric materials. And Kramer's rule dictates that for these materials, their electronic band structures are spin degenerate. That is, for upspin and downspin, their band structures are the same. So we will not get any spin order dependent tunneling or electrical signal as we typically get for ferromagnets, such as tunnel magnetoresistors. We will not see that in these materials. But they're not entirely useless. We can still switch them using spin orbit torque, as shown here. So you can see that charge current is passed through a bottom platinum layer, and that can be used to switch this iridium manganese collinear antiferromagnet. And when it is adjacent to a ferromagnet layer, it can imprint its state onto that layer using exchange bias. So you can read out the state of this antiferromagnet through effectively using the ferromagnet. But now this introduces several problems. So since the ferromagnet is back, the stray fields are also back with it. The ferromagnet now needs to switch. So the speed is also again limited. And then there's the interface problem. So since this is dependent on the exchange bias effect, so the interface at the antiferromagnet-ferromagnet interface, that needs to be very high quality during growth, and that is difficult to control. So these problems can be solved by using non-collinear antiferromagnets. So non-collinear antiferromagnets, in these materials, the spins are not oriented directly opposite to each other. Rather, the spins are oriented 120-degree relative to each other, and they're sitting on a specific plane, like a 1-1-1 plane. So for these materials, those PT symmetries are not present anymore. So there is no single inversion point, and you can't just translate between neighboring sublattices to reach a net zero magnetization. So since those symmetries are not present, so by again through Kramer's rule, the electronic band structures are no longer spin degenerate. So we get spin splitting in band structures, which is also shown here. You can see that density functional theory calculations can be done to calculate the electronic band structures for these materials. So how to interpret these graphs? So each line corresponds to a different band, and this is shown along high symmetry directions only. The lines, the magnitude of the lines are the energies, and the color of these lines represent the spin expectation value. So what is the takeaway from this? You can see that as we change from the first Néel state to the other one, so changing basically each spin by 180 degrees, you can see that the spin expectation value along the x-axis changes for each band at each k point. So now, this is also true if we were to calculate the Fermi surfaces. So the Fermi surface is calculated from the band structure itself. So you basically calculate the points in the band structure that is equal to the Fermi level EF. And then you project that 3D Fermi surface onto the XY plane. Why the XY plane? Because we are assuming that in a tunnel junction scenario, the electrons will be traveling in the Z direction. And as it travels in the Z direction, it is the k points in the xy plane, or the momentum in the xy plane, that needs to be conserved during tunneling. So that is why the projection, the 3D Fermi surface, is being projected into the xy plane. And here also you can see that as the Néel state changes, then the spin expectation value on the 2D xy plane, it changes sign at every k point. Now, what this means is that if we were to use two of these materials, like in a tunnel junction scenario, we are using vacuum here, but they could have used an insulating layer as well. But you can imagine that the left electrode here is fixed, and the one at the right hand side, the Néel state of that is changing. So if you were to now calculate the transmission probability of an electron tunneling from this side to that side, you would see that the transmission is maximum when these, the two Néel states on the two sides completely align with each other. And when they're completely misaligned, the transmission is low, as illustrated by this figure. So effectively, you can consider this figure, the figure on the left-hand side, as the density of states analog in ferromagnets. So when traveling from the left to right, you can see if this was the left-hand side, this was the right-hand side, then the electrons would not be able to tunnel through, because they can only tunnel through if this red matches red here, and if this blue matches blue here, but that is not the case. So that's where the TMR comes from. So even though the net magnetization is 0 in these materials, we would still get a tunnel magnetoresistance because of these spin split band structures. So that's the readout mechanism. We can also write to these devices using conventional spin torques. So for example, we can use spin orbit torque as shown here, and these are all very recent experimental results. So as you can imagine, we pass a charge current through the bottom platinum layer, and that introduces a transverse spin current that travels through the free layer, which here is platinum manganese 3, a non-collinear antiferromagnet. And when it does that, those spin polarized electrons exert a torque on one of the sublattices, and since all those sublattices are exchange coupled to each other, if one of them starts rotating, all of them start rotating at once. And it is because of that strong exchange coupling is why we get such a fast switching behavior in antiferromagnets. So that's spin orbit torque. Recently, there has been reports of spin transfer torque as well in these devices. So again, like regular ferromagnetic tunnel junctions, you pass a current through the device. So now what happens is that electrons that are like because of the symmetry and the momentum dependent spin splitting, electrons coming to one sublattice are like you can imagine that the three sublattices from the free layer, they all contribute electrons to the free layer, but the sublattice, if you consider them as sublattices A, B, and C, then the transfer of electrons from sublattice A to sublattice A on the other side is going to be the strongest compared to B and C. So that is why the electrons coming to a specific sublattice is also sort of a spin, it has a net spin, and that is where the spin transfer torque comes from, even though the total spin current is 0. So that is why, that is how the spin orbit torque and the spin transfer torque works. So in summary, antiferromagnetic tunnel junctions are able to, can be used as regular tunnel junctions as well, but this is an ongoing research area. Especially the spin transfer torque, the theory behind spin transfer torque is still under debate. But initially, most of the research was focused on explaining how the tunnel magnetoresistance works. So that part of the discussion is pretty much established now. So in future, I guess most of the research will focus on how to make these devices faster now that their reading and writing is pretty much established. The whole point of using these devices initially was to how to replace conventional ferromagnets with faster devices. So that is where future research might go to. So yeah, thank you for your hearing. If you have any questions, please feel free to ask.